So the last thing I want to talk about is simplifying expressions with radicals. We've done this before with square roots, so let's just review how we dealt with this before with square roots. So basically what I like to do is rewrite this with all my perfect squares written. There are a lot of different ways that you can do this, but I think the easiest way is to come up with what are the perfect squares and what's left over if anything isn't a perfect square. So I know that 16 is a perfect square. All right, and I also know that x to the fourth is a perfect square. Really, any variable with an even exponent is going to be a perfect square. Okay, now let's look at y to the fifth. That is not a perfect square. So I basically want to think about how many perfect squares, or how much of a perfect square can I fit into y to the fifth. So y to the fourth will fit in, but then I still have a y left over. So I'm just going to write that separately. And then lastly, same thing with z to the 11th. I can fit in z to the 10th. I know that's a perfect square, but I've got one z left over. So I think this is kind of the easiest way to do this. All right, so now let's pull out perfect squares. So 16 is a perfect square, and that can come out. So 16, the square root of 16 is 4. And x to the fourth is a perfect square, and that can come out. So the square root of x to the fourth is x squared. And y to the fourth is a perfect square. The square root of that is y squared. Okay, y is not a perfect square, so I'm going to leave that alone for right now. And z to the 10th is a perfect square. The square root of that is z to the 5th. You just cut it in half. Now let's look at what's left over. Y is left over, and z is left over. So I've got the square root of y, z left over. And that would be my final simplified answer. Now, if you have a different method of doing this, that's fine. Some people like to write out all the x's. They'll write out x times x times x times x, and while that's a lot of work, it does work. And you just say, okay, I'm taking out pairs, and these are the pairs that come out. I have two pairs that come out, and that's reflected in this x squared. So however you like to do it is fine. I'm going to keep explaining the next few examples the same way that I explained this one. So if you don't already have a method that works for you, this is definitely my way of doing it. So try to use my way, see if it works for you. Okay, this next example, again, is a square root. We're just kind of reviewing what we did in the last unit, in the quadratics unit, with simplifying square roots. So I'm going to rewrite each of these terms. I'm going to rewrite the number as the perfect square that goes into it, so 4, because 12 itself is not a perfect square. 4 times 3 is 12. Okay, now I'm going to look at x cubed. That's not a perfect square. So I'll get as close to cubed as I can and then write the leftovers. So x squared is a perfect square, and then there's 1x left over. And z to the 10th is itself a perfect square. So let's simplify this the same way that we did the last one. So the square root of 4 is 2. That can come out. The square root of 3 is going to stay behind. I'll just circle that, and I'll write it under the radical in a second. So square root of x squared is x. That can come out. Plain old x cannot come out. That's going to stay behind. And then z to the 10th. Z to the 5th can come out. I cut it in half. And what's left over is 3x. And that's our final answer. So my next example is now we're getting into cube rooting something. So we're taking out groups of 3. And you still want to treat this kind of the same way that you would treat it if you were simplifying the cube root of 27, which, yes, this is a perfect cube. For these other ones, instead of cutting them in half like what we did for the square root, we're now taking out groups of 3. So you're basically thinking, how many groups of 3 can I fit into 5? And how many groups of 3 can I fit into 6 and 12? And how many are left over? So I'm going to write this the same way that I did the last ones. So cube root of 27, that's a perfect cube, so I don't need to break it down. X to the 5th itself is not a perfect cube, but I can fit in a group of 3, so basically x cubed, there's my one group of 3, and I've got 2 left over. So there, all together, there's x to the 5th that I broke down. Y to the 6th is a perfect cube, so I'll leave that all together, because 3 goes into 6 twice, and z to the 12th is also a perfect cube. All right, so we're pulling out groups of 3. Cube root of 27 is 3, so that can come out. Cube root of x cubed is x. I can fit in one group of 3 there. And then x squared is going to have to stay behind because there's no groups of 3 in there. All right, now let's look at y to the 6th. there are 2 groups of 3 in there, so y squared can come out. And z to the 12th, there are 4 groups of 3 in there, so z to the 4th. And then what's left over is just x squared. So this next example, again, we're taking out groups of 3. So we're trying to think about perfect cubes. 16 is not a perfect cube, but I can break 16 down into a perfect cube times another number. So 8 is a perfect cube, and that goes into 16 twice. W squared, there are no groups of 3 in there, so I'm just going to leave that as W squared. X to the 4th, well, I can fit 1x cubed in there, but then I've got an x left over. And y to the 14th, let's think about a number close to 14 that 3 goes into. So that would be 12, and then I've got 2 left over. All right, so now let's look at this. The cube root of 8 is 2, so 2 can come out. 2 is going to have to stay behind because that's not a perfect cube. W squared is going to have to stay behind because that's not a perfect cube. Z to the 3rd, the cube root of x to the 3rd is x, so that can come out. X to the 1st, there's no group of 3 in there, so that's going to stay behind under the radical. Y to the 12th, 3 goes into that 4 times, so y to the 4th can come out. And then y squared, there's no group of 3 in there, that's going to have to stay behind. So what stays behind? 2, w squared, x, and y squared, all the things I circled. So hopefully this method is kind of making sense and seems like an organized way to go about doing this. Alright, so now we're taking out groups of 4 here. So I want to think about groups of 4 that go into these numbers. The 4th root of 16 is a whole number, it's 2. So I'm just going to write that, I'm not going to break it down. A to the 8th, there are 2 groups of 4 in that and there are no leftovers. So I'm just going to rewrite A to the 8th. B to the 14th, 4 does not go into 14, but 4 goes into 12. So I'm going to write B to the 12th and then there's 2 leftovers. And then C to the 5th, there is 1 group of 4 in there, so I'm going to write C to the 4th, and then there's 1 C left over. Alright, so let's see what can come out. The 4th root of 16, like I said before, is 2. The 4th root of A to the 8th, you're thinking, how many groups of 4 fit in there? So 2 groups of 4 fit in there, none left over. B to the 12th, 4 fits into 12 3 times. B squared, there's no group of 4 in there, so that stays behind. C to the 4th, the 4th root of that is just C. There's 1 group of 4 in there. And then this is a leftover. So I need to write 4th root of B squared and C are leftover. So our last example is taking out groups of 5. Okay, so the 5th root of 32, hopefully after just even from this lesson you guys have memorized that the 5th root of 32 is 2. Now let's look at A to the 10th. Okay, so there are 2 groups of 5 that fit in there and no leftovers, so I can just rewrite that as A to the 10th. B to the 7th, 5 does not fit into that evenly, so I'm going to write B to the 5th because 5 does go into that, but then there's 2 left over. So the 5th root of 32 is 2. The 5th root of A to the 10th, there are 2 groups of 5 in there, so I pull out an A squared. The 5th root of B to the 5th, there's 1 group in there, so that can come out. So these came out. And then this is all that's left over, the 5th root of B squared.